Okay. Let's start the class. Okay. I need to close. Today, I will like to study further on energy method, which is very important. Okay. Several problems in final exam will be from this energy method. Okay, so it is important to understand the final exam. I mean the energy method, and I hope that you fully exercise the energy method through task 10, which was not easy to solve, but I want to re-emphasize that how powerful the energy method is can be applied to any kinds of a beam problem. Not only beam, it can be applied to structures and torsions, any structures under any load and any kind of deformation. So it is a very generic and applicable to design of most of the structures. So energy method. And simply, as you know, the older strain energy is the help of the sigma x, epsilon x, and the sigma y and epsilon y, and so on. And this is a volume integration. This was obtained from considering the spring, like the spring, the strain energy is simply half of the force and half multiplied by the deformations. Anyhow, this is a strain energy. And for the beam, we do know sigma x equal moment. Moment is a function of x, and EI. EI also can be a function of x, of course. I'm sorry, not the EI, it's I, and times y. Y is a vertical distance. And epsilon x is simply sigma x divided by Young's modulus. Of course, the Young's modulus can be also a function of x. And then and we put it there, and then we do some integration. dA is simply dV is cross section dA and dx along the cross section and the length. So for the beam, the above equations can be much simplified, in you can say EI and moment x square and dx. Pay attention to the fact that no longer a volume. We just have need to integrate along the x, okay, along the x from all of the beam, and all the cross-sectional information came into this I. I is moment of inertia. So all you need to do is just integrate dx. And of course, this EI, bending moment of inertia, can be a function of x. And so if you have some divisions, and you can simply say some of these beam and I and EI and moment I and Li, each divisions. So for example, this one and that, each one, say, you can say L1 and L2 and so on. This can be a certain moment which can be assumed as a constant, and E1, a moment 1 and moment 2, and this is a EI1 and EI2, and so on. So this is the A strain energy. And now, using this strain energy, let's try to solve some typical problems. For example, let's say we applied a certain P here, and at the same time we apply the moment, concentrate moment and concentrate the force. And then this structure will simply deform, right? Deform. So this will have I will rewrite here. This will deform like that. And amount of this is a delta, and this is the a theta, right? So this is a delta and this is a theta. And please pay attention to that. Moment zero can generate delta and theta, right? And P0 also can generate delta and theta. Okay, so the last task I was asking was that you apply the P0, and then you can calculate the delta, or you can calculate a I'm sorry, I need to change this one as a theta and delta. Okay, so when you apply the P0, you can certainly calculate delta or theta. And also, when you apply the M0, you can calculate theta and M0. So either one will cause a theta and delta. So how do we get this theta and delta when we have this P0 and M0? The energy method says theta is simply a derivative U with respect to M0, and P delta is a deflections, and which is the delta is a derivative U with respect to P0. So this one is a force, and delta is kind of pair, moment theta and P0 delta. But that doesn't mean that P cause only delta. P can also cause the P0, I mean delta and theta, and M0 can also cause a theta and delta. But this equation, please attention to this formula. This equation says only delta and theta corresponding to a moment. So for this case, okay, this particular case, what you need to do is that we need to have the moment as a function of x, right? Because we have a moment of x. For that purpose, we have to have this reaction force at the end. So we, due to this P0, we will have a P0 downward, and moment 0, we have a M0 like that. And then moment at the x, say for example, at the x here, and there is a positive directional moment, which is a moment x. And how do we get this one? Well, moment x is simply obtained using equilibrium, right? So moment x is that m0 and minus p0l, because this is the downward, and we have p0 p0x. And another important reaction moment at the end will be there will be a p0 times l, right? Because this p0 will cause the moment at the length l. Okay, so the directions, we always need to be careful about the direction. This is the direction, p0 times l. Okay, so I will rewrite this term first, and plus p0l minus p0x. Okay, that is the function of moment function of x. And moment 0, p0 l minus x. Now we are ready to go ahead calculating this theta and delta, because we have all the information we need, mainly moment as a function of x. So let's perform this derivative. Let's say we want to calculate the theta. Okay, the theta here, theta at the end. So from these equations, theta, moment m0 and u, but to do so, is convenient to use the chain rules. So simply L, we use the derivative, okay, derivative L, so moment derivative, u derivative, and then moment derivative with respect to m0. This is simply a chain rules. So u, because using this one, and we can derivative with respect to m, which is very easily obtained, moment x, because this is a 2, and derivative and ei, right? And then moment x, now moment x is here, derivative with respect to m0. We have only m0 here, so we only just 1, and dx. Okay, so let's perform these integrations. And as you can see here, moment x, okay, I'll write down here, m0 derivative L, okay, we just do integrations, and plus, and P0L square, and minus half P0L square, and divide by the EI. Right, I did integrations. So this is the like that. So here we can see that EI M0L and plus half EI P0L square. That is the theta. Okay, that is a theta due to M0 and due to P0. Now, very interestingly, what if we only apply the P only? Okay, only we apply the P. We only apply the P, and then we want to calculate the theta. Okay, but theta, as you can see, we have to derivative u with respect to M0. So we have to assume this there is M0 and get all the equations. And then final, we have to say M0 equals 0 because there was no M0. And so this will be P0 L square half EI. This is the rotations due to a P0. Okay, so this is a kind of tricky, but very important procedures as well. And to get a theta, okay, theta due to P0. Of course, we can obtain the delta due to P0 using simply this one. In that case, we don't have to apply the M0, right? And also, we can have a theta when we apply the M0. So we only apply M0, and we can get a theta. In that case, we don't have to apply the P0 because we simply can use this formula. But when you calculate the delta due to M0, okay, we have to use the equation, but there was no P0, so we have to apply a fictitious force, as we did. We applied the a M0 when we calculate the theta. So we calculated this one, and then last we simply say M0 equals 0. Okay, so that we can calculate P0, how the theta due to a P0. Okay, so please do remember these procedures and the most important point in energy method. So basically, you can calculate all the deformations or rotation, any point you like to calculate, regardless the regardless of all the loading point. And now I like to solve. Okay, we obtain this theta is like that. Let's confirm this result using just conventional method. Okay, conventional method means that we just solve the beam equations. So let's say we have a beam and subject to a P. And governing equations of this beam problem, as usual, is EI V 4 times the derivative with and Qx. Qx is simply a pressure, the distributed load, which can be given as a function of the x. So this is a Qx. But in this case, Qx equals 0. No distributed load. And important point is the boundary condition. Boundary condition here is the v equals 0 and v prime equals 0. V 0 means that no deflection. V prime equals 0 means no angular rotation, no rotations. That is the condition for clamped. And force, vertical force means that there is a moment equals 0, moment equal EI, V double prime equals 0, and V is the minus EI, V triple times the derivative, which is now given as a P. Okay, so simply this is the differential equation and external load, distributed load, and these are 4 boundary conditions we have to consider to solve these differential equations. Well, we do have a 4 boundary condition. We have this 4 times the derivative, and you will see there will be a 4 integration constant, which will be solved using these 4 boundary conditions. So we are ready to go. Let's solve this one and simply integrate one time, which will be now constant, integration constant, and then one more, and second, C1x plus C2, and one more times, and C1 x squared plus C2x plus C3. And EIV, and then 6C1 x3 plus and half x squared plus C3x and C4. Okay, so here are the final integrations, and this means a deflection, this means a angle, this means moment, and this means shear force. Okay, so using this 4 boundary condition, we need to obtain this 4 integration constant. So here is the x equal L 0, and here is x equal L. And at x equals 0, let's put it here, x equals 0, 0, 0, 0, and this C4 equals simply 0, right? And V prime is here, x equals 0, 0, 0, and C4, only C4, and this has to be 0. Now, this EI with triple times, this is simply this one. So, this one is a minus P, and this one, and as you can see here, and C1L plus C2 equal simply 0. So all C1 equal minus P, C2 equal P times L, right, from this, and C3 and C4 is simply 0. So these are the solutions. Now the theta at the end, theta at x equal L can be obtained from this. This is nothing but V prime and equal and C1 L square from this and plus C2L divided by EI. Okay, what is the C1? Well, C1 is minus P. And what is the C2? P times L. So this one, and then simply P minus P L square plus twice, no, and P L square, right? So as you can see that this one is a EI help and P L square. This is the theta at the end. So as you can see that this result is exactly same as these equations. And you can see that energy method is very much straightforward without considering much about the boundary conditions, much about differential equations. Whereas you have to, using the differential equation, you have to start with this fourth order differential equation, which is a governing equation for any generic beams with all boundary condition, always a four boundary condition, which will be used to solve all the integration constant C1 through C4. Okay, and the final equation is the same as the one by the energy method. So as you can see that this is a method called equilibrium equation or differential equation or energy method. Okay, energy method is basically integration equations, integral equation. Well, another method you can use to solve this beam problem is a 3D beam. As I mentioned, this 3D beam is based on this energy method. So which one you like to use? Well, understanding the equilibrium in differential equation is very important to understand all the what is going on inside the materials, equilibrium and stress strain and all the geometric compatibility. But also energy method, you can see that very powerful and which can be used for programming and can be solved, which can be used to solve all kinds of beam problem using computer simulations. Okay, so now I like to extend this concept to more interesting cases. I like to list, for example, EX example. Okay, say you have a beam, and then you apply the concentric moment. Okay, very simple. And now, let's say we want to calculate how much it deflects. When you apply the moment, we certainly have a certain deflections delta and rotation theta. So let's say how much the delta we will have. Well, nothing. Now you can solve these equations using and solve this delta using energy method. Okay. Of course, you can solve this differential equation as well. So this is a very simple another simple example. Okay. Another example will be, say, now we have a beam, and then you apply either P or M0, any force. Now you want to calculate how much the delta, because this beam will deflect. continuously from 0 to L, and you want to calculate the deflection at a certain point, for example, L over X, half positions, and here also it rotates, right? So this is the delta, this is the A theta. How will we calculate this delta and theta using energy method? Well, for this purpose, you always need to apply a fictitious force where you want to calculate a rotations and deflection. So here you can apply, for example, fictitious F, and you can apply a fictitious moment. I would like to use a different symbol, okay? MF means fictitious. Fictitious force or moment, and PF. And the real force is P and moment. Now, we want to calculate a delta and theta. We need to apply this point. Why? Because the theta, based on the energy method, we always given by the PF. And delta at here is always given by the energy method and MF. So to calculate the deflection and rotations, you have to have a fictitious force where you want to calculate the deflection. So you need to apply this PF and so on. For that purpose, of course, the step is the moment function of X, which needs to be PF and MF and P and M, right? And then when you say here, you need to apply PF is a fictitious force. We didn't apply, and you simply set 0. And here, of course, at the final, you have to set the moment equals 0. Okay, so this is the another example to solve this deflection at the different location from the point you apply the load. Okay, another one, another example will be, say, you have two different beams connected and with the different cross sections properties. So this you can say EI1 and this is a EI2. And then as before, you apply the force P or moment 0. And now you want to calculate deflections here or rotation, deflection here or rotations. Any place you want to have. Okay, this is the another important case where you can use the energy method. Again, energy method will simplify the whole procedures. All you need to do is when you integrate to U, okay, you can be integrate. Say this is the one division and another divisions, and you can divide into two parts where you have a EI1, EI2, and this is a moment and function of X and moment function of X. So in this region, this EI1 can be constant. You can out of this term can be out of this integration. This can be out of integration. So from this example, you can simply extend the concept, and you can have many different beams connected together. So whenever, let's say, you have a very continuous, well, continuous, you can also discretize them into several or as many as you like to consider. Okay, so as you can see that this concept can be extended to any kinds of a beam, even for the wing. Wing has the cross section can be very low. Okay, just 1 second, please. Okay, so well, I want to emphasize again, there are several problems in final exam and relate to this energy method. 다음 주에 기말고사에 이 에너지 메서드를 이용해서 문제를 푸는 게 몇 가지 나와요. 상당히 중요한 메서드입니다. Okay, so I hope that I fully covered this energy method. Now I'd like to go back to a buckling problems. Okay, in here, buckling, I just explained the typical behavior of the buckling when it happens. Well, simply the buckling happens in structures where compressible load load is present. So there are some interesting phenomena I will explain. Okay, definition of the buckling or some behavior of the buckling. As I mentioned, please keep that in mind that the buckling always occur where the compressive stresses or compressive load occurs. Okay, so in this beam, okay, first one is in this beam, we apply the force P, and we do know that this beam and the top part is in each cross section we have a moment as a function of x, right? And any cross sections, top is the tensions and bottom is the compressions. So tension and compression. So if we look at this, the bottom part, if you look at the bottom part, there is a certain amount of compressions. Okay, so the bottom part becomes very unstable. So it simply wants to this originally it was a straight, originally straight, but it wants to buckle, right? So if we consider only bottom line, you can see that this one is subject to a compression and it simply move to a different position, which is the typical behavior of the buckling. And if we consider only one beam, okay, one beam, something like that, and subject to P, and this one is a very typical case, is called Euler buckling. Euler buckling, and under compressions. And then I would like, if we plot this P versus delta, delta is this, and P versus delta, and there won't be any delta, meaning that this under compression is simply a force increase, and then reach a certain point, it buckles. Okay, and certainly a lot of delta So this is the point we call critical. Okay, critical point. Critical load. Okay, P critical. So we have to design a beam. Sometimes the length, sometimes the thickness, not to reach P critical. So we will, the P critical is a function of L, and function of this cross section is if it is very thick or very thin, so it's a function of a bending moment of bending stiffness, EI. Okay, so this is the another buckling case. Another interesting case is that we call snap through. Snap through. Initially, the beam was a bent like that. Okay, pre-bent. We call pre-bent. And then we start to apply the force P vertically, and then this beam will like to deform and may reach flat positions. But compared to our original positions, the length in beam direction has to reduce, which means that there will be a certain amount of a force P. I mean, not the exactly force P, but a certain amount of a compression force. I need to say certain, is not the same as this P, but a certain amount of a compression force. So in these positions, the structure becomes very unstable and doesn't want to stay there. It just wants to change the configurations, so go down. So initially it was like that, and when we apply the force P, and then it suddenly changes the configurations when this force reaches certain point. So this called a snap through, and this is used for the switches, electric switches, and you need to have a two positions such as on and off, and this is the commonly used for the electric switches. Okay, so all from this simple example, you can see that they occur when the structures are subject to a compression, more or less. Well, of course, this critical load, can be obtained mathematically for the given beam length L and beam bending stiffness. So there is a, I will rewrite this definition of a critical load. Again, the critical load is the point which would cause buckling. When the force P reach some critical load, it will buckle. Buckle means that this one suddenly a buckle, suddenly deform a lot. So this is the delta. So if we increase and no delta, but when it reaches peak critical, it will buckle. Very important point is that this peak critical is much lower than yield strength. Yield strength, you simply a yield strength times cross sections, which is yield strength. But this buckling simply occurs much lower than this yield strength. And for example, this is a crane, and there is a lot of weight here, and these structures will subject to a significant compression load. And don't design just based on this yield strength. Why? Because these structures will mainly buckle, right? Mainly buckle, which will like this, and this. So we have to design this P critical so that we can have how much the length and how much this a cross section will be. Why? Because this P critical is a function of this L and function of bending stiffness of this EI. Okay, so so this is the important fact you need to understand. How will we get this formula? Well, we have to do so. We have to go through some equations, and I will briefly explain what we need to consider. Okay, what we need to consider to consider this buckling loads. Okay, this is the a conventional. Okay, I will redefine this case. This is the V, and this is the V plus dV, which is the very typical case for in driving the beam equilibrium equations. And this is the left-hand side. There's a moment, and there is a moment plus the moment. And there is a distributed load Qx. Now, vertical force equilibrium says there is a dV Q dx. And moment equilibrium says V dx dm, right? So from this, we can see that dV dx equal minus Q. And the moment equilibrium, we have dm dx equal minus V. So these are two equilibrium. But here, as you can see, we didn't have any P here, right? We didn't have. But what if we have a P? See, that is the another point, additional terms we want to consider. Compression force. Why does it make the difference from this case? Well, certainly there is a distance, and there was a P here, P here, P here, and this is the here is the V deflection, and here is the V plus dV. So this is a distance. Difference is a dV. V is a deflection. Okay, V is a deflection. So in equilibrium, force equilibrium is the same as before. But moment equilibrium, there is another additional moment caused by this P times P to the distance dV. So we do have additional term due to pressure P. So imagine that when you compress compressive, this dV will increase and increase, and it gets worse and worse. So that's the big difference between the case when we don't have any P, right? Imagine that we apply a positive force. Okay, if we have a positive force, just to change the direction. This one, well, is simply is P and dV, and V will be smaller and smaller, and the contribution of a P will be okay. So this term, when P equals 0, it will cause the buckling, and P if is P positive means a compression, okay? Because we indicate this one as the compression. Usually this is the negative, but in this case, this considered as a positive. So this one is the tension case. Okay, simply in the case of tension case. There's a no buckling. Okay, no buckling. So any structure, say compression, this structure like to buckle this way or that way, very unstable. But if a structure has the tension, then it's the no buckling, very safe, no buckling. So any structures on the compression, again, you have to consider a buckling. So combining these two terms, and now we have a differential equation, and we have an additional term due to compressions. Okay, this is the 4 times, and this differential equation is different from these differential equations, and again the main term is because of that. And solving this differential equation is not as straightforward as before. Before, when we don't have the P, all we need to do was to just integrate 4 times on the left-hand side and right-hand side, but we do have this term, so we cannot integrate them. So we have to have a homogeneous solution and particular solution, and this is the engineering the integration constant. I don't want to go through these differential equations, but simply please remember that we have a 4 boundary condition here, 4 boundary condition here, and then P doesn't contribute to any boundary condition, which means that we have a non-trivial solution. Okay? Non-trivial solution. Trivial solution means that we do have certain deflections and without considering any boundary condition. So anyhow, this is the final equations. Okay, through these procedures, we get these boundary conditions, and please, you don't have to go through these derivations, but you simply do know that boundary condition and differential equation, but final, you get these terms. I will redefine the problems. Problem was that this AP, well, this way or that way is actually same way, right? Don't think that they are 2 different problems. They are the same problem, but anyhow, we have a length L, beam of L, and the cross section we have a EI, and P critical now is proportional to EI. Imagine that EI is increasing, the P critical load is also increasing. Well, that makes sense, of course. And if you increase L, imagine what happened when increase L. Well, P critical will significantly reduced, right? In other words, let's compare this case and same. Which one can easily buckle? Of course, this one can easily buckle, which means that P critical will be very low. And now let's compare this case. Same length but very thin. Which one will buckle easily? Of course, this one buckle very easily because EI is very small and P critical can be very small. So all you need to remember is that this EI proportional to EI, L square, okay? Please pay attention, square. So this is the equation you need to have in mind. And P and delta and B critical and okay, so this is the critical buckling load. So as you can see that when you design the structures, when you design the structures, you consider what? Well, there is a P and cross section A, so stress will be P over A. This has to be less than yield strength, material strength. Well, this is a certainty case. Okay, certainty case. But as I mentioned, this buckling will be very high value. So buckling will happen much lower than that load. So this one, you need to consider that, but also P critical load. So here, P has to less than A times sigma L. But the P may buckle without any material failure, as mentioned, EI and L square. Okay. So if you plot them as a function of L, and this equation is a constant. This is called yield strength, and so A times sigma Y, and this is a constant independent of L. And now this P critical is the L square. So if we plot this, we get this equation. So for this is the A safety zone. We need to design it here. If we go here, material will fail. If we go this region, and the structure will buckle. Okay, so above here, material will fail. So don't go here and don't go here. Only safety zone is this much. Especially if the length is get longer and longer, we have to consider this buckling load. Okay, so in most case, the buckling can happen much earlier than material failures. Okay, that is the very important fact we need to consider. Okay, so that is the brief what I like to cover today, and as I said, tomorrow I would like to go through all the subjects, so you need to prepare for the final exam. I just want to remind you that that we have a major chapters we cover this semester. In the midterm, we had to go through all the basic stuff for these advanced topics. So midterm, we went through only equilibrium and temperature and displacement conditions and so on. But I like to emphasize that in final exam we will cover thin wall shaft. Thin wall shaft is the like a thin wall, or this is a closed and opens, or this is the I-beam also open. So this is a thin wall shaft. Thin wall shaft. Shaft means this is the a subject to torsions, right? Torsions. So thin wall and all the shear flow. You know how to calculate the shear flow, right? And this is very important point. And issues in beam, what it means that this is a sigma x moment I and y is the bending stress. And now you have a unsymmetric beam, unsymmetric, and also shear center, okay, and which can be complicate, which may need a complicated procedures to get the solutions. But more importantly, we need to understand the concepts, why it happens, and how to solve it. What's the physical meaning? Okay, and bulkily, as I mentioned, P critical is proportional to always EI L square. Okay, under compressions, and this is a concept. Now, energy method is the as I mentioned, we always need to get some strain energy, and then we get a certain derivative. Okay, derivative. You need to do some derivative to get the certain delta or angle. If this is a moment, this will be angle. This is the force. This will be the deflections. So energy method is very powerful, and there will be a importance, and you will see several questions in final exam. And another one is the how to use 3D beam. Okay, 3D beam procedures, and what to specify, and so on. And of course, you don't use a 3D beam, but you need to understand how to use a 3D beam in detail, so that you can answer all the questions related to this 3D beam. Okay, basically this is the topic we will cover in this final exam. Okay, so tomorrow we will spend 1.5 hours to discuss or answer your questions related to prepare the final exam. Okay. So I will complete today's class, and hope that you have a chance to review all the issues for the final exam. Okay, so if you have any questions, ask me through Kakao group talk. Okay, that is much easier to communicate rather than question and answer in this Zoom conference. There are a lot of noise in here. I hope that to solve in next semester. Okay, anyhow, thank you, and then talk to you tomorrow. Okay, bye.